Imagine a future where your failing heart, lungs, or kidney can be replaced within a few months by a brand new, fully functional organ. Luckily for the more than 114,000 Americans currently on the national transplant waiting list, artificial organ technology is emerging as a permanent life-saving solution. As humans live longer and chronic disease rates rise, the need for more available and compatible organs has intensified. Hence, the dream of developing artificial organs made from mechanical or cellular sources has been a target of considerable medical research and experimentation. In this presentation, Mark, Josh, and I are going to define and provide an overview of different types of artificial organs, discuss both existing and prospective examples of artificial organs, and examine the future trajectory of artificial organs in medicine.
Although modern technologies are beginning to stray away from mechanical artificial organs, a variety of these methods are still worth noting. One of the most prominent procedures in terms of mechanical transplantation is to replace a dysfunctioning heart valve. This process can correct and prevent issues such as valvular heart disease, stenosis, and regurgitation. These mechanical valves have been proven to be extremely durable and able to withstand the strenuous workload of the human heart. Different artificial polymers and textiles have been used in the creation of different valves, cusps, and sinuses. These processes are often very complex, including multiple steps of pouring and freezing molds, as well as combining them to articulate with the patient's organ. Another method used in this process is heterografting, which describes the process of removing a valve from an animal, such as a pig or cow, and implanting it into the human's heart. Homografting is a very similar method, where valves are removed from human cadavers and used as a replacement for a faulty valve. Mechanical heart valve implants have seen a rise corresponding with the continuing problem of heart disease in America. In fact, St. Jude recently announced that they had surpassed 1 million implants. The implications for this process are incredible, as technology has followed suit with the improvements in valve implants. More high-tech imaging software has been developed to produce higher resolution images to catch heart disease sooner. Also, robotics are being implemented for more standardization in surgical procedures, especially those that are considered routine. Another area in which mechanical artificial organs can be implemented is the replacement or repair of the trachea. This procedure has received far less attention than manufactured heart valves. However, the story behind these inventions is fascinating. Tracheal reconstruction has fostered serious enthusiasm from the pulmonology community, but in the clinical setting, there has not been much success to speak of. Interventions began with the use of glass tubes, Marlex mesh, and silicone in an attempt to reconstruct a dysfunctional trachea. Attempts were first made on dogs, however later seen clinical attempts on humans in critical condition. Due to the lack of successful outcomes, research shifted gears towards implementing living tissues, preserved tracheal homografts, and even transplants. These methods were heavily limited due to the sheer lack of donors. Currently, mesh prosthesis is the method most heavily experimented on. There are great opportunities for advancements in this field, however the lack of surgical application of the technologies is a serious issue to be addressed moving forward.
A principal organ is an artificially constructed device that is manufactured specifically for organ replacement, which is designed using 3D printing techniques. These principal organs contain a wide variety of biomaterials including metals, composites, ceramics, and polymers which help to stabilize the organ and provide structure. To continue, the process of developing a 3D printed organ includes first taking a CT scan or MRI that provides the precise dimensions of the tissue that will be replaced. Secondly, a blueprint must be created by making a virtual design of the intended organ. Next, the organ will then be printed in a sequence that mimics the natural biological process of embryonic cellular fusion. Finally, a printing device will construct and release the material, which has been described as being almost liquid or gel-like in texture and having the consistency of a toothpaste. A few examples of 3D organs can include printable limbs, the bladder, eyes and ears, and even a heart and brain. As it currently stands, the cost of a typical kidney transplant can cost roughly $330,000 according to the National Foundation of Transplants. However, bioprinting is becoming a more cost-effective option as a conventional bioprinter can retail for as low as $10,000. In addition, 3D printing artificial organs can help to reduce the need and wait time for organ donors and reduce the risk of the organ rejecting a new host after transplantation. To continue, scientists have also run into a significant hurdle in regard to 3D printing organs. This problem is termed as vascularization because scientists are having trouble trying to replicate these unique and intricate networks of blood vessels that carry oxygen and potential nutrients deep into the organ while simultaneously removing harmful waste products. The blood supply issue is problematic because it must be solved before 3D printing can reach clinical trials and be discussed as a legitimate option.
Tissue regeneration is currently a common artificial organ intervention for bladder and heart valve substitution. Scientists use the patient's own cells in conjunction with biomaterials to regrow the organ outside of the body. Tissue regeneration begins by extracting a small piece of healthy tissue from a patient's deceased or injured organ. This can be as small as half of the postage stamp. The tissue is teased apart and grown in culture to produce large quantities of the appropriate cell type. Next, a biomaterial scaffold is shaped to form the matrix of a desired organ, and it's seeded with harvested culture cells. The organ is placed into a device that provides conditions mimicking the human body and stress tested to ensure it's strong enough to be placed inside the patient. In the time frame of a few weeks later, the engineered organ is completed, and surgeons are able to implant it back into the patient, attaching it to the in situ portion of the organ. The biomaterial scaffold will disintegrate within a few months, leaving the patient with newly regenerated tissue. However, this approach does not work with all organs, as there are certain cell types that cannot be regenerated using these techniques. Although there has been tremendous advancement in artificial organ technology, scientists are still working towards bioartificial organ prototypes that are generated from the cells of prospective self-donating recipients. By harnessing the technology that transforms normal body cells into stem cells, researchers are able to rebuild a heart or lung for transplantation. This method involves 3 steps. First, researchers acquire a deceased donor organ and decellularize it by hooking it up to a pump that digests and washes off all the cells, leaving behind an acellular organ matrix. This donor organ is now a collagen scaffold that can provide the tissue backbone for cells to repopulate and assume normal function. Next, using a recipient's own stem cells, scientists grow up the various cells that the organ will need to be fully functional. Finally, these cells are added to the donor scaffold and placed in a bioreactor that stimulates reseeding and functionality of the organ by making it expand and contract, like a working heart or lung. This organ would then be implanted into the recipient, avoiding organ rejection, immunosuppression, and circumventing the problem of a donor's organ shortage.
Now that you are more familiar with some of the processes behind artificial organs and the methods in which they are created, it is time for some critical thinking questions. When considering the United States demographic changes, why do you think the demand for artificial organs has increased within the last decade? Also, what are the financial benefits of finding permanent alternatives to traditional donor organ transplants? Remember, current mechanical heart transplants are only an expensive and temporary, yet very life-saving fix.